Hey class, Adam Ward here. I want to talk to you tonight about the Streeter-Phelps model. This goes along with lecture 21 out of your Chopra textbook. And so I want to start tonight with our model of dissolved oxygen and biological oxygen demand, for which we use a capital L as the symbol. And so for a simple CSTR where we've got BOD and oxygen to keep track of, we might set up a model that looks like this, where we've got BOD being lost due to settling, and we've got both oxygen and BOD being removed from the system by the actual decomposition of the organic matter. And so as we've done multiple times in the past, we also add the reaeration constant here, that Ka, which is basically a diffusion of oxygen into the system from the atmosphere. And we can write out a mass balance for both of these. So BOD with inflows, outflows, and that reaction loss, which of course is a combination of settling and decomposition. And then for DO in the system, we can write that same mass balance. From left to right, those terms are inflows, outflows, decomposition loss, and then that reaeration exchange described with Ka. So we know that dissolved oxygen and BOD are linked by oxygen deficit. This deficit we've described a bit in the past. It finally comes into play with this lecture. It's how far below saturation we currently are. And so this is a big advance in the Streeter-Phelps model, where rather than modeling BOD and oxygen explicitly, instead what we're going to model is deficit, or how far below saturation we are. We're going to essentially take ourselves out of the business of modeling oxygen levels and into the business of modeling deficit, or how far below saturation we might be. So I want to just give you a sense of how this works with both a closed system and an open system. This follows Chopra from the textbook. So for deficit, we'll use a capital D. And if we had a closed system, so simply a bottle that we filled with water downstream of a wastewater treatment discharge, for example, we'd have this reaction, Kd, and the decomposition of BOD creates deficit in the system. So as BOD concentrations decay exponentially, we get essentially an exponential ingrowth of deficit. Right? So the exponential loss of one generates an exponential growth of the other. And we know that oxygen levels through the system have done something like this. Again, deficit representing the vertical distance from that dashed gray line down to the black line that I've drawn in that right panel. So that's a closed system. If we think about an open system, much more typical for us, you can see that now deficit lives in between two reactions. So deficit is created by decomposition, and deficit is removed by reaeration. That's a key concept out of this web lecture that I want you to remember. Deficit is created by decomposition, it's removed by reaeration. So BOD still looks the same in this case, exponential decay. For deficit, we get a pattern that's more characteristic of an exponential loading, because it's that middle species in a series of reactions. And then oxygen gives us that characteristic sag and recovery that we know will exist in our Streeter-Phelps models. So, one more time, just to reiterate, decomposition described by Kd creates deficit, reaeration removes deficit from the system. So deficit is in many ways the opposite of oxygen. Deficit's not consumed by decay, it's created. It doesn't enter from the atmosphere, it more or less leaves to the atmosphere, or it is replenished by oxygen entering from that atmospheric boundary. So for a CSTR, we can use our BOD model just like we have in the past, first order exponential decay. But for deficit, our model is going to look just a touch different. And so, sparing you the mass balance, I'll go right to the explicit solution here. And I want you to notice a couple of things about this solution. One is that it looks awfully similar to what we did for exponential loading back when we did particular solutions for a single CSTR. The other I want you to notice is that you've got two competing reactions in series. Kd that's generating the deficit, and Ka that's removing the deficit. So although this is derived for a specific example, this really just matches that exponential loading case that we looked at in, I think, lecture 4 of the textbook. The final thing I'd like to look at tonight is how this would apply to a plug flow reactor subject to a point source of loading. And so we'll measure x, the downstream distance from that point source as usual. For BOD, this is our classic first order advection and decay model. So we've seen this solution plenty of times. For deficit, the model looks a little bit more complicated. And essentially this model has two pieces to it. So that term on the left is any deficit that you had flowing into the point at x equals 0. So how much deficit was there upstream? That's basically that general solution that we've talked about in the past, working its way downstream. This big ugly term on the right is almost identical to the CSTR response that we derived on the previous slide. So now we can take solutions from a CSTR, we can apply them to our plug flow reactor, and we can see that really it's just the general solution and a particular solution concepts that we've been using throughout the semester. Now, finally tonight, I want to just talk briefly about how to get that D naught that we had on the previous page, or that deficit right at the point source. Classically, we would use end member mixing when we were working on any other compound. That doesn't exactly work for deficit, and I want to talk about why. Deficit is measured relative to that oxygen saturation level. And we know that that is not constant, but that's a function of temperature, partial pressure in the atmosphere, and salinity or total dissolved solids in our system. So because temperature, because salinity, and ultimately saturated levels are not constant, neither is deficit. And so it's not too bad to deal with, but we've got to really think through this rather than just trying to do end member mixing on deficit. That's a sure way to make a problem. So, 4 key steps here. First, we're going to mix temperatures together. Same way that we've done end member mixing, simply treat the temperatures as concentrations that you've used in the past. In fact, temperature really is just a concentration of heat per unit volume, and we'll get to that in, I think, 4 or so weeks of class. So we'll do end member mixing on temperature. We'll do the same on dissolved oxygen, so the same end member mixing that we've always done. Now that we've got a new temperature and potentially a new salinity if we needed to end member mix those together as well, we can calculate a new oxygen saturation level. So given our temperature, calculate a new saturation level, and then given our new saturation level from number 3, our new oxygen level from number 2, we can calculate a new deficit. So I'd encourage you to try this for yourself and actually prove that you can't mix deficit and you can mix oxygen and temperature and calculate a new deficit. So at this point in the lecture, you ought to be able to do 4 things. First, you should be able to describe the differences between and the relationships between deficit, dissolved oxygen, and BOD. You should be able to write the Streeter-Phelps equations for a CSTR, so those mass balance equations. You should be able to write those for a point source into a plug flow reactor, and you should be able to calculate deficit downstream of that point source by using the mixing technique outlined on this slide. Thanks for staying along, everybody, and I'll see you in class.